Good morning, all. Okay. So today is next second day of our statistical workshop, and thanks again to HBCH RC Muzaffarpur, TMC Muzaffarpur, and particularly Dr. Kumar Prabhash and Biostat team with Ankush. Today we'll be having exercise that we talked last day about different statistical test, preliminary statistical test. So here we'll be having some data example. We will touch how different data structure look like, and then we will see how to manage and how to get data analysis over there. Yeah. So Akash, have you joined? And Vendra, I think I can see Vendra has joined. Yeah. So then over to you, Akash and Vendrila.
Yes, sir. Thank you, sir. So in this session, we'll be doing the hands-on for the examples we shared in last slide. Me myself will take it through an Excel narrative, whereas Vendrila will share the SPSS data, creation of it, and how to create outputs and the results in the SPSS.
सामने से है चीजों को एक थर्ड पर्सन की तरफ से देख और वो अभी इतना अंदर आ चुका है तो अभी मैं हर एक चीज को वैसे देखना शुरू कर दी
I think Ankush, someone need to be silent.
क्या हुआ था आराम से लगाया पापा उधर पानी के पापा क्या है तो वो आराम से
Mr. Apurva, could you mute yourself?
I was totally different.
Let's start, Akash.
Yeah. So I'll share my screen. Hope my screen is visible. So can me and Andrea together share the screen? Is it possible? No. Yes, no, right?
I am sharing my screen.
Let's see, side by side it can be presented.
Screen is visible?
No. I guess we cannot do that. Sure, we'll start with it. Then we can.
Now my screen is visible.
No, I guess. Only my screen is visible. Okay, yeah, your screen is visible. Where is mine? But I guess people can do the tab change above. Can everyone see that there is one tab and another tab, two tabs? Hello?
Yes, yeah. Akash, start on that.
Okay.
Yeah, we can see. Okay. So here we can see that you opened Excel file. So let's start with some first Excel file where you can show this first the data structure of it having. Yes.
Yeah.
So
So we first.
Mandirala, hold on. Let Akash explain, and then we will come on it. Okay.
Yeah. In the slide, we had this one example, as we all saw. It is from the paper Prevalence of Iron Deficiency Across Different Tumors and its Association with Poor Performance Status, Disease Status, and Anemia. Okay, so in this, we had used one sample t-test against the WHO threshold. So we were just comparing hemoglobin, its mean, against the threshold value. Okay, so here what we had is we had one cohort of patients. For example, for now we had one cohort of patients of women for which we have the hemoglobin status, and we'll be comparing it with a reference value 12 G per DL. Okay, so if we see the data here, okay, so this is the data, but this is not for men or women. We don't have that information yet. We just know that this is for women's. Okay, so this is the hemoglobin value, and we need to compare it with a reference threshold, which is 12. Right? There are no such two groups, nothing. It is just one cohort of patients in which we have an hemoglobin group, hemoglobin values, and we need to see its mean, what it is, and that mean is similar to the threshold or not. Okay, so what we would do is we would do normal averaging. So we will take a normal average of it. Okay, normal standard deviations we can calculate in Excel. Count is the number of counts we can calculate. That since this is t-test, so in t-test we actually calculate t value, and based upon that we calculate the p value. Okay, so this is the formula for calculating the t value. We don't have to go to the formula. We just have to show. I just had to show you that such t value has to be calculated before t value, and then from that we have t dot distribution dot to absolute b3 b12 1. So this value helps us calculate the t-test. Yes.
Maybe just to add one thing that before Mandirala jump to this analysis. So basically, this is sample of 8 individuals, and their HB value, hemoglobin value is been given. So from here we can easily calculate their mean value, right? Maybe it is going to come 8.5 or 9.5, whatever it is. But point is that, or hypothesis or statistical test is that we are trying to see what about mean value is coming that is significantly different than overall or population level mean value or not. That is our first concern. So null hypothesis is that these 8.5 or 9.5, whatever mean value from 8 individuals are coming, that exactly or near to similar with population level mean value, let's say 10.5 or not. If it is significantly different, then as Akash said, we will get p-value less than 0.05. P-value is a byproduct of this t-test. So don't get confused, T and P. P-value is a byproduct of t-test. And we are going to apply t-test to see that 8.5 or 9.5, that whatever mean we are going to get, that is some standard or given population level mean value over there, that is different or not. That is that context over there. Over to you, Mandirala.
I guess my screen is visible. This is the data of 8 patients and their hemoglobin level, and we are using one sample t-test here. So I think.
Before jumping for analysis, could you show that how the data view would be there,
yes,
variable view would be there, and what does it mean? Why patient and HB having two different icon over there given? One is having 3 circle and another is having scale. Why this is?
Suppose in Excel, whatever Akash has defined, we have to first create the same data in SPSS also. But in SPSS, we can see there is 2 columns. The hemoglobin, one is patient and the another is hemoglobin level. This format is SPSS data view format. If I go to variable view, here I can see that there is a different type of columns. Name numeric, read, decimal, values, missing columns, something like that, and measurement. That is nominal, one is nominal and one is scale value. When we are considering our hemoglobin level, that is actually numeric plus that is having also values after points. So in that case, we are considering 1 decimal values. We have mentioned here 1. But for patient, we are considering patient data has only nominal value or numeric value, because patient data are here number wise, and after that we have mentioned is in such a format that both will be continuous, like patient and hemoglobin level, and after that we have read this data or imported this data. If I need to import any Excel sheet from in SPSS, then in that case I have to do file import data from Excel, and after that I can click on the Excel sheet also, and if I click open, then I will get this value.
So it is basically the data formation which matters. So in Excel, what we showed was as per the example mentioned in this slide, the data was as the patient series and hemoglobin values that we actually have, which is each row for each patient, and it has each values as well. For those, we have manually calculated something. However, this data management is optimal management. The same data structure needs to be there for SPSS or any other statistical software for this particular testing or doing hypothesis testing for such kind of data. So just understand the kind of data. It's an observational study where we have 8 patients, and for 8 patients, we have the hemoglobin value in for each row presenting each patient. So the way it was presented in the slide, the way it is presented in the Excel, the same way it will be presented in the SPSS format as well. So that's how the data should be to perform any analysis. This way you can do the statistical analysis in Excel. However, in Excel, we get limited towards calculating till t-stats or p-value by manual things, and we need to know the internal functions of Excel to calculate this, which is a bit of a hectic thing rather than, and this is not a statistical software as well, as we all know. That's where Andrila switched to SPSS, and she showed you the data, which is again the same format as required, because this is the way we can do the analysis on such kind of data. And this is now easily able to be analyzed for t-test. So now she will show the t-test application on this data. Can you show, Andrila? So in analysis, we have various tests laid down here. You can go to compare means, where we have various means comparison tests. One sample t-test is one such. You can select that.
Akash,
Yes.
hold on. Somebody want to have some points.
Okay.
Yeah, suppose if we are importing an Excel file to SPSS, the variable view sheet will also get updated automatically, or by default we have to update, or manually we have to do something in the variable view sheet of SPSS.
No, by default it will come, but it will SPSS will try to assess that what kind of variable we entered in Excel. Based on that, it will by default it will give some type or character over there. But later on, if you want to customize, for example, you want to change from nominal to numerical, you can do, but you don't need to do every time. So it will automatically take by SPSS once you import data from Excel to SPSS.
Okay. Thank you.
Can you? Yeah.
Yes, Akash, carry.
Can you continue? Yeah.
Yes, Akash, please continue.
Yeah, one sample t-test. Andrila, please continue.
Yes.
So here it will ask you which variable to be taken for the testing. We take the HB level for testing. We have certain options and various things. In options, do we have anything? It's just a confidence interval that what it should be presenting. We set 95. Continue. Yeah. Test value will be 12 here, right, sir?
Yeah.
Okay.
So let's say we are going to give some test value.
Yeah. So in the output sheet, you will see the output of one sample t-test, where it has shown us the number of samples, mean of those samples, standard deviation, standard mean error, standard error mean. Then you can see the t-test t-value calculate here by default, degrees of freedom, which is used to again calculate the p-value later. Significance two-tailed, which is the p-value here, which tells us the mean which we got, 10.462. Is it equal to or not equal to the reference value that we gave, which is 12? And the mean difference that we got from 12 is minus 1.53, and the confidence interval for it is given as well. So based upon this, we can say that the mean that we achieved, 10.462, is significantly different to the reference p-value, reference hemoglobin value.
So
It's
here
not equal.
the test value is going to be considered as 12. So basically test value means we are assuming this some hypothetical value or some population value that we are assuming it is around 12. So we are going to test that distribution of 12 hypothetical value or the hemoglobin level value around 12, that distribution is forming, that is similar with 10.46 that we are going to get from 8 patient or not. That's basically, it's not that we are going to exactly going to make neck to neck comparison between 10.46 with 12. No, we are going to have this hypothetical value 12 having the distribution, same type of distributions followed by our sample of 8 patients or not. For example, if you shift from 12, here you can see there is a significance difference is going to come. But instead of 12, we can have 2 options more. Let's have quickly before jump for another test. So do one for instead of 12, let's say how if you put 14 and even if you put 10.5, what happened? Let's see. Yeah, see? So it is going to be much more significance difference. See? Earlier upper lower if you put your cursor earlier one, we can still see lower interval was minus 2.1 to minus 0.96. Now it became minus 4.1 to minus 2.96, and the mean difference also became raised from minus 1.53 to minus 3.53, and it's becoming much more significant about because earlier we already reached significance level. That's why it's very difficult to identify how much more significance are coming, but still we are having much higher significance value over there. Now one step more, Akash, do something like, yeah, perfect. Let's say 10, yeah. So see, we now drop down our significance level. Okay, Nina asks, how do we get the test value? Okay, in this case HB. So yeah, so that's a good question, Nina. So basically we can get from published data, from other literatures, other articles, or you can have some anticipated value or arbitrary value we are going to think it. So there is not any calculated value or data value value obtained from your data. That's not required. It's either you can substitute this test value by from a published article, somebody else done some research, their work, their mean value we can consider and take it forward here as a consider as test value. Akash, over to you. Akash, you are mute now.
So this is how the t-test work for an observational data or any kind of cohort data if we have and we need to compare it with any kind of threshold or anything reference value. So let's go to another example, which is one test, and second we had was independent t-test. Independent t-test, this example is from lung cancer in never smokers, a review. Basically in this, what they were doing is, do never smoker with NSCLC differ from ever smoker in age, at diagnosis, tumor size, and other presentation characteristics. So we have smokers group, non-smokers group, and we just want to compare the tumor size between those people. So how do we compare? So since the smokers, and non-smokers, they are independent of each other, and the values coming from them are independent as well. We may call it as independent two-sample t-test. Okay, so each patient is independent of each other anyways, but here we have two groups, smokers and no groups. We say they are two different groups and we are comparing the values from those groups. So the data represented was in such kind of this format. In Excel, if we could see, it is in same way only. Yes, sure. Yeah. Yeah. So in Excel, also it this way. So if I want to make a record or something, how a layman person would be recording things, right? What I will do, I have a smokers group, I have a no smokers group, and I will keep this smokers group in one group and non-smokers in one. What I will do is I will calculate its mean, average kitna hai iska. I might do it this way. I might calculate the averages for two groups. I might say there is a difference between mean. So smokers may tumor size is big, non-smokers may tumor size is very small, and I can make some
sorry for
conclusion.
interruption. Could you
Yes,
share
sir.
your screen, because it's showing this, SPSS is coming still.
Spaces.
I will stop sharing for some time.
Oh. Okay.
Yes.
Is it visible? No? Yeah.
Yeah, please.
Yeah. So suppose in a layman person is doing it. So what I will do is I will for smokers मेरे पास 8 patients थे, 7 patients थे, उनका values डाल दिया. Non-smokers के लिए I did this way, and I did their mean calculations by here average करके for this, and I will do some differences, or directly I can say that this has smokers have higher tumor sizes, non-smokers has lower tumor sizes, and I will make some conclusions. In Excel, we can do this using the formulas of T dot test, where A2 to A8, B2 to B8 to 2. It is basically the tails which we mentioned. So as last we spoke, there is two hypothesis testing, two tail and one tail. So for two is used here for two tail. So that's how we can do. But this is not the correct way of analyzing data or to maintain the data, right? However, the data should be like each row should be independent patients, whether it is smokers or non-smokers. So that's how the data should be, and that's how it should be used for analysis. And that we will show in the SPSS format that we have now.
Before jumping on SPSS,
Yeah.
there is some data structure issue, because see, we are having two columns like smoker and non-smoker. Ideally, column name should be HbA1c value, right? And then it's not the smokers; it's a group of smoker are having HbA1c value. So that is why Akash said that this is not the correct structure or the correct way of capturing the data. But as already Oindrila opened the file, it shows that correct structure where we are having, three column. First column is this ID number or serial number, followed by hemoglobin level, and third category, third variable as they are having smoker and non-smoker. So eventually you can calculate t-test or p-value over here, but to be honest, this is not the correct approach or correct data structure. So aligned with this correct data structure, now over to Indrila. Show.
Yes.
Akash, stop sharing, then Indrila can start sharing.
Yes.
Now, this is the data structure actually. This is contained. I guess my screen is visible.
Yes.
This data is containing 3 columns: serial number, HbA1c value, and smoking status of those person. Here, while I will consider to walk you through variable view first, because here serial number is also numeric, and HbA1c value is numeric, and smoking value is also numeric. How it is supposed to be numeric? When we can see that there are properly string value. If we click this button also, then I can see there is a numeric value in the smoking column. What I have done in this data set, I have first imported the data from Excel, and after that I have restructure this column, smoking column, in such a way that I will able to analyze the data also, and the side by side I will be able to see the status also of the smoking column. If the data is not numeric, I will not be able to analyze the data with some string values. In that case, I went to variable view. After that, suppose I have written one for smoking cases and 2 for non-smoking cases. In variable view, I have changed the values, like 1 value I have assigned as smoker and 2 value I have assigned as non-smoker. After that, I click OK. And such a way, my data value is like that only. If I am clicking this button, it will show what is actually the levels of that smoking status column. And this one is the smoking status value, and HbA1c is obviously a continuous numeric value. That's why it is also showing the numeric and scale value here. In my data view, this is my actual data view after importing the data from Excel. And then I will go you through how to analyze the independent sample t-test. It is analyzed compared with independent sample t-test. I have already checked that. So suppose
Andrila, can you just rename it like it is tumor size so people will get confused? So we can see we can rename it as well in this data, as we all know. It's tumor size. So let's keep it as tumor size.
Thanks, Akash, for identifying it is tumor size. So basically, this what we are going to test is that what is the mean tumor size between smoker and non-smoker. So smoker and non-smoker, both groups are considered as an independent group, and in this independent group, their mean tumor size is same or not, that is going to be tested. So that's why Indira is going to have analyze and then go Indira go analyze and then go to compare mean, and we are going to pick independent sample t-test. So independent sample t-test, our test variable is tumor size, and grouping variable is smoking status, like smoker or non-smoker. And here we need to define group. Yes, so already defined as a group 1 and group 2. I think you have to make it as a 0 because your code is given as a 0, right? Not 1.
1, 2, sir.
Okay.
It's 1, 2.
Carry on then, yeah.
In options, we can say 95% confidence interval.
So based on that, we will be going to have even in next step, we can replace this 95 to either with 90 and 99%. I can see that how difference values are going to have. So this is 95% confidence interval she consider. Now click on OK. Yeah. Yes.
So here SPSS gives a very defined output where it also describes the data with mean, standard deviation, and then it gives a detailed comparison as well. So about the equivariances, would you explain also?
Yes, so there are two assumptions fundamentally. So first of all, we are going to compare mean between smoker and non-smoker. That first table is showing that 7 people are smoker, 7 people who are non-smoker, and their mean value was 4.6 and 2.91 along with the standard deviation. So we are going to have compared this 4.6 is significantly different than 2.91 not. But there is some another additional assumption that's going to play a role over there, that both these groups are having equal variance, means equal standard deviations as or not equal standard deviation. So that is an additional assumptions going to play a role over there. So in this context, these two assumptions also by default being tested, like in table 2. One assumption is equal variance and another is unequal variance. Unequal variance don't give you the significance value and p value, but you can see this equal variance assumption is going to give us the significance values. That second or third column is there, that sig, it's going to give you as 0.051. So that's mean we are almost significantly different, provided that lower and upper confidence interval is going to have 1.14 to 2.23. So that's the first row we are going to consider our test statistics results. Significance, that is in terms of the p value should be significance. If you put the crusher over there, Vendrila, where significance is going to have? Yes. So significance is this 0.051, and then jump last two columns like yes, 1.14 and 2 points. So these are the lower and upper confidence interval. And if you go to two-tailed test, also going to have 0.000. So that's also going to have this significance difference. And the mean difference is, it's absolutely this absolute mean difference means 4.6 minus 2.91. That's given as a mean difference 1.6968.
So just a question to the observers, like since the p-value is less than 0.05, which is significance as Sir said, what do we conclude? The means are similar to each other or different from each other?
Anyone can comment?
So the tumor size in smokers and non-smoker groups is significantly different, or is it equal based upon the p-value? Hello?
Yes, Swahani, please tell.
Do we say it?
It's getting muted again.
So do we say it is similar?
Similar. Okay.
No, we should not say it's a similar. We would say it's a significantly different.
So can I get with an hypothesis example? So for example, here H0 is one our hypothesis, H1 is one our hypothesis. So what is H1? H1 is like tumor size is similar in smokers
And non-smoker.
and non-smokers, right? So my screen is visible, right?
No, it's
I
Andrila's
will stop
screen is
there.
coming.
Now you're screen.
Yeah, so H0 is what? Tumor size is similar in smokers and non-smokers. Similar, we may say, or tumor size mean, we can say for now then. Tumor size mean is similar in smokers and non-smokers. H0, what will it be? Opposite, right? So H0 will be tumor size mean is not similar. You can write any kind of like similar, not equal, right? In smokers and non-smokers. So what happens when p-value is less than 0.05? P, if it is less than 0.05, we say that reject H0. Let's not go into this terminology a lot. We will just say if p-value is less than 0.05, we will say that we accept that, or we reject that tumor size is similar in both group, and we accept that tumor size is different. So if p-value is less than 0.05, we would say the tumor size mean is not similar in both groups. Okay, and whichever is high-low, we make that assumptions. For in this case, where we got, Andula, can you share your screen?
Yes.
Okay, in this scene where we are getting tumor size smokers is 4.6, non-smoker is 2.9, and p-value is significant. So if it is significant, we are going to say that the two means are different from each other. Okay, now what is less, what is high? Since smokers have high tumor size, we can say that based on p-value, means tumor size in smokers is significantly higher than that of mean tumor size in non-smokers. Equivalent to tumor size mean is different in smokers and non-smokers. Okay, so P less than 0.05 always leads to like positiveness of our H1. Like H1 is true, we can say then. Okay, and H1 is what? We always want to prove that there is a difference, there is an increase, there is a decrease. So here we may not say that it is similar, we will say that it is different, and that in smokers it is significantly higher. Is it clear? If there is anything, please do ask. Because the technicality always confuses a lot. Is it clear?
Swahani?
Repeat it once again, sir.
Okay. So
Okay.
what I did was just start with a simple hypothesis creation. And what I did was we just stated one hypothesis. So what would be the null hypothesis here? That tumor size in smokers and non-smokers is similar. Okay. Here, particularly, we are going to make assumption based upon mean. So we are stating as tumor size mean is similar in smokers and non-smokers. Okay. What is our aim to say? Ideally, what it is, we see that we should be proving that being smoker, tumor size would be higher, right? So
Yes,
that
sir.
becomes
Yes,
our research question. And that's how our alternate hypothesis gets created. So we say that
yes,
tumor size in smokers is definitely not similar to the tumor size in non-smokers. That's what we want to prove, right? So that is our
yes, sir.
H1.
Yes,
And that's
yes,
why
sir.
we created this and we tested, we got a p-value less than 0.05, which tells us that reject H0. Whatever the null assumption you are creating, reject it. Your hypothesis
Yes,
is correct now, H1. That
yes,
there
sir.
is a significant difference. The difference with Ontula showed no here. It is bit difficult in Zoom, but yeah, now I guess you can see. Yeah, the difference which is shown here, 1.6857 mean difference in the second table, 1.68, which tells that this difference is significant. The difference is not equal to 0, it is higher something.
Yes. Now, Andrea, just quickly, could you change this confidence interval level?
Yes.
Only replace from 95 to 99 and 90, and let's see how things has been changed over there.
Excuse me, sir. Hello.
Yes.
Sir, one problem is creating that two screens are shared at a time, and
Yeah.
the who is speaking that their screen is not visible, and different one's
Okay.
screen is visible. At a time, two screens are shared because of that.
Yeah, what we will do is, Antila, do you have your that Excel sheet?
Yes, I have
Which I
that
shared?
Excel.
Yeah. Please open it. I will stop my sharing because she has the SPSS data which should be seen. That is main.
Yeah.
So she will share the Excel sheet.
Yeah,
Thank
so
you.
now
And
she is going to have with 99% confidence interval. Yeah. So see, our earlier in comparison to earlier confidence interval. So here, it become 0.92 to 2.44. Go up. What was earlier one? See. So lower was 1.14 and 2.23. Now the lower become go down 9.92 to 2.44. What does it mean? And now go to again, Indira, replace from 99 to 90. Then let's see. Yes. So see, it is now having smaller one, right? Difference between lower and upper is been quite lower now, 1.22 to 2.13. Whereas earlier one was go up, it's gone. Okay. So earlier one was, quite bigger over there, 0.92 to 2.44, and earlier one was 90 was in between. So you can change these confidence interval levels, that window, by replacing, by considering 90, 95, and 99. By default, we always consider 95, but just for illustration purpose, we can change it as well. Yes. So if it is now independent, it is done. Now let's go for next one.
Yes.
so we have the paired t-test. So here I have the question. is it the correct representation of the data? So there is A, B, and C columns. One is the patient IDs. Second is the CA 125 value pre. Then it is post CA 125 value. And there is a difference. So difference we have calculated, that is. So do you think this is the correct representation?
Some background. So basically for ovarian cancer, pre-treatment that their CA 125 value has been given. And then after post-treatment, just a minute, after post-treatment, their CA 125 given. So here see, instead of serial number, we put it at patient. So basically ID are going to be same. The same individuals been represented as ID 1, 2, 3, 4, 7, and their corresponding p-value is there. So remember, the first time when we are showing this type of data structure, we are showing that smoker and non-smoker are having hemoglobin level. So that, and then we said that that's not correct structure, because under smoker and non-smoker column, we can't put the hemoglobin level value. But here, we put the PA1, CA, pre-CA 125 and post-CA 120. So basically, the same column name been taken over there, and under that, we are kept their value. So in this context, this is the correct approach. This is the correct structure over there. So keep it in mind, because it makes much more sense how you are preparing your data, how you are structuring your variables. And again, here, in case of smoker and non-smoker, individual were different. That's why we said that's not the correct. But here, these are the same individual. That's why we can retain this pre and post CA value parallelly over there. And after that, we are going to make the simple mean, pre and post difference value from individual to individual. And we are trying to see that the mean difference between this pre and post treatment are same or not. So first, once we talk about independent t-test, we consider some arbitrary value like 12 with compared to 10.46. But here, these two groups mean are going to be compared.
And here the group is basically the time. So hence it is called paired data and can be analyzed using paired t-test. So in SPSS, if we can see, there is the same way the data has been incorporated, and you can also see some missingness manually incorporated there, where we have for the 8th patient, the pre data was not taken and post was taken. Hence the difference wasn't calculated. Similarly, for the 9th patient, we had the pre data, but the post data was not there, and hence the difference was not calculated. This brings the ambiguity where this patient's data wouldn't be used for comparison, right? So a lot of QOL data you would have seen, pre-post data you would have seen, baseline, after treatment, you are taking readings and everything. If there is a missingness, that is not going to help you or test your hypothesis, make any conclusions. That's what it will be shown here now. And this is the way the data has been formatted. We can see here also there is row-wise the patient's data entered, and for each patient data, there is a pre and post. So that is the perfect way of making the data like paired data or longitudinal data or follow-up data, what we usually say. So until I will do the analysis and show these cases. In same analysis, analyze compare means, we have the paired t-test option. You can put the two variable pair one, variable 1, variable 2, pre and post. Save the confidence interval. You can see here the similar way the descriptives is given, the mean at pre, mean at post, the n numbers used for analysis. As we saw, there were 9 patients data, and since there was missing in between, the software used patients data which had both the time data available, which is pre and post available, that only it has used. The missing ones are by default not considered. Since it's a paired data, there is some correlation, right, between them, because it is of the same patient. Each patient is bringing some kind of correlation in it. So that's why a correlation is calculated here as well. in most of our exploratory analysis, or where you are trying to look for pre and post, there is any difference or not. Correlation a lot may not matter here. Now, for your case, when you are going to summarize your results into something, you would directly go for the paid t-test data table, where you have the differences calculated for the pair pre and post. The difference is 658.57. The standard deviation of the difference is this 154. Standard error mean is 58.32. 95% confidence interval, again it is given. You can see the difference is not using zero. It is not having zero in between. So that says that your data is very much significant. T value again calculated, DF again calculated, and the last is the significance two-tailed P value. So which tells that there is a significant difference between pre and post of CA 125 levels in ovarian cancer patients. You can make this assumption from this. So yeah, is everything clear or some question? P value tells whether the difference.
No question.
Okay. So this is what a comparison of pre and post looks like. If you have any kind of data, it's just CA 125, you may have a lot of biomarker data, tumor biomarker data, and a lot of blood related data sets, values which you would look for. You can use this test to analyze such kind of data.
Yes.
Okay. Let's go forward.
Yes, sir.
Yeah. So all these tests that we saw, one sample t-test, two sample t-test, paired t-test.
Hello.
Hello.
Yeah, suppose we have 100 samples, and let us consider in real world we won't have all the data for all the patients, right? So what should be the minimum number of samples to have an effective result? It should be 70% of good samples we should have, or 90% to consider for any statistical test.
So that is entirely been supported by calculating sample size or power calculation. So whatever the statistical, one thing is the analysis we are going to show you here, but in you can consider the study broadly in two ways. One thing is prospectively, you are keep on recruiting patients and observing their value, or you already having data of retrospectively you are trying to calculate the compare the values. In the both the way, what happened that it's quite natural that you raise the point, and that's quite relevant. We see that 100 patients who have started to look upon, and maybe at one time point or before treatment you are having for all 100, but next time point, post time point, you don't even having more than 70 or 60%, and that might happen because data not captured properly, patients not turned around, many reasons could be there. So now point is that analytically, could you calculate this? Yes, we can calculate it. We can calculate the mean comparison. As far as this pair t-test is concerned, that should be done only for 60 people. Those are having both time point observations, not for 100 people. Only 60 people patients observation will be compared. Second point is that is it adequate or not? That could be done by either by power calculation, if you are having retrospective data, or if you are having prospective, you are going to collect the prospective data, you are planning in such a way. So then you need to have proper sample size calculations. Keep it in mind that you can lose information, patient data. So then we will be having some structural, some number, adequate number that we are going to go say that you have to calculate with 70 people at least, or let's say 120 people at least, to reach your 70 or 80 number people that can be compared. So that is completely scientifically would be judged, and we are going to deliver talk in future on sample size calculation separately.
Yeah, thank you, sir. This is very good question was, and as sir said, you have to prior decide and do the power calculations and then decide for the samples. And yeah, you can calculate on any samples if you want to test, as largely it has also been said like it is statistical analysis, it's always a garbage in, garbage out, unless you know if you are doing the correct thing, right? So that's how now we are going to transition from one test to this all test which we did today. Now this was parametric test thing, and what it was like, the parametric test is valid if the data is data is right upon some assumptions. For example, normality, as sir last section said, like if the data is normally distributed, you go for the parametric data analysis, right? That's where we use this analysis or these testings. Now, second test what we are going to see is Mann-Whitney U test, which is going to be applied on similar kind of data, like continuous data compared for two groups, right? However, this is another approach, and here mean is not much valid. Why mean is not valid? Because you might not have that many samples of data. Your data distribution is not going to be normal, and then you will be transitioning to this non-parametric testing analysis, right? So now that we have this data, we can do is, in the previous test, we can just do this normality testing of two group comparisons. Indrila, can you do this? Can you go to SPSS once? Okay, group Mann-Whitney, not Mann-Whitney, this one. Not Mann-Whitney.
This one is Mann-Whitney.
Two group test. What was independent t-test?
Okay, independent t-test.
Okay.
This one.
So what we will do is we'll do this analysis. We'll assess it for testing which kind of test can be applied, and then we'll apply the correct test as we mentioned. So now, can you just go to analyze, descriptive statistics, explore, take tumor size in one and factor smoking in factor. Yeah, plots, normality with plots. Continue. Histogram, can you take the histogram as well? Histogram. Yeah. So we'll just assess the distribution of data. That will also answer your question where the data is number. This is not going to be the number of samples affecting any test, but it is about the distribution. So now you can see we have this tumor size distribution for smokers and non-smokers. Can you go to the test of normality table? These are the histograms. I stop here. So there are two tests basically, Kolmogorov-Shapiro-Wilk test. These are for normality testing. So based upon this p-value, what we are going to assume is whether the data is normally distributed or not. If it is normally distributed, you are going for t-test or something. If it is non-normally distributed, you are going for Mann-Whitney testing. This also underlies one of the assumptions like sample size, as you said, like for lesser sample size, your data is not going to follow a lot of normal distribution, right? Then you might go for Mann-Whitney testing. So means won't be the correct representation or comparison way. So, but here you can see, so both the tests are showing normally distributed. How the hypothesis works here is, here the H0 is, here it is reversed. Like we say, null hypothesis is normally distributed and alternative hypothesis is non-normally distributed. And when the p-value is non-significant, we go with the null hypothesis. Okay. And we say the data is normally distributed. Hence, we did the t-test here. Okay. If this would have been non-normally distributed, we would have gone for Mann-Whitney test. And somewhere sample size also takes part here, where a lot of time we say that if n is more than 100 or n is more than 30, the data tends to be normally distributed and we can go for parametric testing and everything. But most of the time it is not true. We need to do testing before doing or suggesting which test. And since this being small data, it is normally distributed. So t-test is adequate for this. And we can do Mann-Whitney testing on this as well. So Andila, can you go to the Mann-Whitney analyzing of this data itself?
This data?
No, this is, I guess it is having ranks. So we will continue with this testing only to the Mann-Whitney test. So analyze non-parametric test. yeah, so there is there is legacy dialogue. There are a lot of tests.
Hello.
Two independent sample tests. So as two independent t-test it was, this is two independent Mann-Whitney tests. You can say. Grouping variables smoking. Define. Continue. Okay. Okay. Descriptives, yeah. Descriptives and quartiles you can click on quartiles itself. So this is more of the descriptions what we needed. Okay. Continue. Yeah. So to replace t-test, if the data is non-normally distributed, you can go for Mann-Whitney testing. And Mann-Whitney, what it does is it calculates rank in the data. It gives rank to the data and calculates the U statistic, and based on U statistic, it calculates the p-value. It's different than that of the t-testing. So and here it compares a lot of, there we say mean is compared to between the two groups. Here we say the distribution is compared between the two groups. And that's how the tumor size p-value Mann-Whitney U-test is given. And the asymptotic significance total 0.02, so which is significance, showing that the two distributions are significantly different. And mostly while doing this non-parametric testing, we would use median and interquartile range for representation. Can you go a bit up in the descriptive table? Here we have medians. Yeah, you can see the median is given 3.65 for tumor size. It is for, okay, this is not the correct calculation. It has done is both the variables it has done. It has not given group wise. You can go to the descriptive table above below. Or again, you can go to the explore. Explore. Wait, in the statistics, M estimators. Continue. Percentage also you can click. Okay. We just want to see for two groups how the median and interquartile ranges are. Lower table, lower. So this doesn't have this quartile. So here the percentiles table, if you see, there is the median, 50th is the median, 4.7 in smokers, 2.9 in non-smokers, same as that of the mean, I guess, right? It is similar because it is normally distributed data. Median is equal to mean a lot here. And then you can see the interquartile range, which is your 25th interval, which is 4. And upper is 75th percentile or third quartile, we can say, which is 5.1. Similarly, for non-smoker, it is 2.7 and 3.1. So a lot when you do this Mann-Whitney test, when your data is non-normally distributed, you represent your data with median and interquartile range for both the groups, and you can make the assumption similar to that of the means, but which we made, but using the median values, or you may say the distribution of the data. So that's how the Mann-Whitney test comes in replacement of independent sample t-test.
Yeah.
When the data
so
is
in nutshell, sorry for interruption. So
Yes,
in
sorry.
nutshell, if you by default choice is independent t-test, provided your data is following normality. So you can go jump with that and you can go for independent t-test and make these assumptions that null hypothesis both groups are same, and alternative they are not same, means their mean are not following the same distribution, or the data is not following same distribution, and you can go for independent t-test. If you fail to get that data is not following normal distribution, so that's having by QQ plot, and there we are anticipating the significance value. It is if your value is significance below 0.05 for normality test, then alternative is Mann-Whitney U test. This is exactly so. whatever that statistical tests are there, like independent t-test, pair t-test, and other, every statistical test would have alternative non-parametric test. So if every test need to be performed provided your data is following normal distribution. If your data is not following normal distribution, there is an alternative choice as non-parametric test. For example, now we explain as an alternative of independent statistical t-test is manually u-test, and then we are going to have the comparison. So while we are going for non-parametric test, so we are trying to avoid the mean-wise comparison, because our core idea is not to make the mean comparison. Idea is that the distributions are same or not. Okay, so that's why we are trying to avoid for non-parametric. In non-parametric, to avoid insist of mean, we are trying to get median, we are going to have percentile, and all the other parameters been taken care to make the comparison insist of mean wise comparison. Mean definitely would be presented over there, but in terms of the p-value and other comparison, we also take it forward on that. So until now, we have seen these two basic comparison. One is independent t-test, pair t-test, and then in non-parametric we are having man-Whitney test. So now the final one will be having this alternative of pair t-test, that is in context of the non-parametric. What is called? Akash, would you finally touch this?
Yes, sir.
Alternative of pair t-test?
Yes, sir. Yeah. Sorry for a bit distracting. Okay. So we have for now, similarly as that we did for t-test, we had independent t-test. But independent t-test, we had Man-Whitney U-test for comparing between two groups. Similarly, what do we do when our paired data, which is pre-CA 125 and post-CA 125, non-normally distributed? We would have gone for Wilcoxon sign rank paired test. So a bit of heavy word, but yeah, Wilcoxon sign rank paired test. It can be used when your data is non-normally distributed. And for the pair, how do you test for normality? You don't go and test the normality for pre and post. You will look for the differences between them. Is it normally distributed or not? Okay, because all of the statistic uses is the difference it uses. So Ondila, can you go for the data again? So in this data, wait, please. Sorry. So here we have another example, pre-QL data. In Excel, can you go once? Sorry. Yeah. Here, development of EORTC questionnaire module to be used in quality of life assessment in head and neck cancer patients data. So mostly the quality of life of head and neck cancer patient data, we use quality of life data from C30. If you can go a bit below, the clinical question is that, do EORTC QOL C30 global health and symptom scores change significantly within head and neck cancer patient after radiotherapy? So before and after, overall quality life values, are they significantly differing or not, changing or not? So since the data is very small and it is probably not shown the normality assessment being normal, so we have thought of using Wilcoxon sign rank test for comparing this pre and post quality of life data, and we would see if it is normally distributed. So in the data, if you can go SPSS, and this is the correctly represented data pre-post for each patient. We will check the normality for this difference for now. Ondila, can you check the normality for this difference values?
Sorry, you don't need to check the normality, no?
Normality, explore.
Okay. So.
Yeah. So here we can see the data p-value is more than 0.05, which tells the data is normally distributed. Yeah, the differences are normally distributed. And hence we can use the paired t-test for comparison, and which is the correct one. But however, since so we just have to show you this Wilcoxon sign rank test, we would use the sign rank test example here as well. Okay. Can you go for the analyze? Yeah, again analyze. Now we will go for non-parametric column. Yeah, non-parametric. 2 related samples. Here we have 2 related samples. Wait, a bit slow. Yeah, pre, then post, and then Wilcoxon sign rank test. Okay. Okay. Descriptives and quartiles, but it is no use because it is giving not by group wise. It will give now because we have 2 variables, pre and post. Yeah, so pre it has given the mean, minimum, maximum, median value 58, which is 70 and 60, which shows the quality of life has reduced after radiotherapy. The median was 70, then it has gone to 60, and the interval, which is IQR, is 65 to 80, 55 to 65. That has also reduced significantly. So if we cannot say that the intervals are at least overlapping or something, it is very much differentiating. And this is the ranks in between calculated to calculate the test value and then the p-value. You don't have to go into that mathematics for now. The test, the asymptotic significance two-tailed is 0.05, and it is borderline significant, or we may say it is not significant. Better to say not significant. So here we say that though the quality of life has reduced higher, 70 to 60, it is not significantly reduced.
Akash, I think Suhani want to say something.
Yeah.
Suhani, want to have anything?
Yes, sir. So in SPSS, how do we calculate quality of life? Like, just give me an overview, small overview.
Okay. So quality of life data. Are you talking about particularly with URTC quality of life or anything else?
Sir, WHO quality of life.
Yes. So so that is basically having multiple subdomain. WHO quality of life would be having multiple subdomain, and
Yes, sir.
then for these subdomain need to be compare. If you're trying to assess between pre and post, so then you need to compare subdomain wise first. Let's say you are having 5 subdomain. I can't recall actually how many subdomains are there in WHO quality of life. Let's say you are having 5 subdomains. So 5 subdomain would be having pre and post comparison, and then make a consolidated remarks that, okay, out of 5 subdomain, 3 and 4 are having no difference, or one are having significantly high and low. So that's the way. But in addition to that, one crucial point to having that, anyway, we are going to make the comparison, but before jumping any comparison, we need to show about the mean value as pre and post. And here we are trying to assess this comparison with respect to only 2 time points. That's why you are saying as a pre and post. But if you are having multiple time points, not only pre and post, after post also having multiple time points, so then we can't go with this independent or pair t test. So that it should be some additional statistical test need to be captured over there. And in upcoming lectures, we will try some other alternative structural requirement over there and how to make it. Yeah.
Okay, sir. Thank you so much.
Alhamdulillah, can you go to the Excel sheet once? I just want to type the hypothesis for normality, sir, because it is a bit reversing. So here, can you just put H0 as normality testing hypothesis? H0 is normally distributed. Normally distributed. H0 is normally distributed. And H1, you can put it as non-normally distributed. Because the null, why we have taken normal distributed, because in ideal situation we consider that data has to be normal in real life, right? So here null is always your normal distributed, and hence when the p-value is significant, if p-value is less than 0.0 is more than 0.05, if p-value is more than 0.05, we conclude data is normally distributed. Okay, that's what the simple thing is. It's a reversible thing from that of what we do for normal testing hypothesis. Normality hypothesis is this way. So yeah, we'll share this sheet and PP data as well. Second is one-way ANOVA. We just quickly go as we been short of time. So one-way ANOVA, where do we use? As we spoke last time, when we have to compare continuous value, suppose the tumor size value in between more than two groups, right? So 3 or 4 groups, if we want to compare some continuous value or tumor size value, how we would be comparing. So ANOVA brought this kind of testing.
So sorry for that.
Yes,
Again, in Shwani's context, if you are having multiple time points of quality of life, so one of this next step would be ANOVA that we are going to touch by Akash. When we are having multiple groups and multiple time points over there. Sorry for Akash. Please continue.
Yes, sir. So this is here the Excel representation as what it was in our slide, that number of observations in each group of low risk, intermediate risk, and high risk is given here. And in each of the risk, what is the value? So it was the data from biochemical outcome after radical prostatectomy, external beam radiation, or intestinal radiation therapy for clinical localized prostate cancer. So do biochemical failure rates or pre-treatment characteristics difference across the 3 risk groups defined by PSA? Okay, so we have these 3 risks defined, intermediate, low, and high risk. And in this, we are going to check some characteristics or values. ANOVA, the low the value is like PSA, I guess. Can you just click on the Excel?
I guess failure rate times.
No, rates, how it could be. Can you go in the Excel sheet again? Excel. Highly significant for PSA and 5-year PSA failure survival. Okay, so this is the PSA values in both the intermediate risk groups. So can you go up above? So these values we are going to compare, but this data it might seem a bit of good representation for Excel, but for analysis perspective, it is not the correct way. As we did for two independent tests where we have smokers, yes, no identified, and their values. Here we should also have risk identified in one column, and another column should have the PSA values. Okay, Ondula, can you show the SPSS sheet now? So this is how the data should look like for each of the patients' values and their risk groups. So since we have more than 2 groups, we need to use ANOVA here. You can first do the normality testing as we did earlier for this group as well. We might now proceed directly to show the testing. So once and here in one-way ANOVA we have in compare means. Can you click on this? Yeah, the risk we have already given here. Okay. So independent, we'll have continuous, and factors we have the categorical. Okay. Yes, wait. We have some contrast here. Some So ideally, what is here our assumption is we have three groups, 1, 2, and 3. The values are different in three groups or not. We have to compare, right? So ideally, the hypothesis, what it does, there is one parent hypothesis, which does is mean is equal in all the groups, null hypothesis. And there is alternate hypothesis, parent hypothesis is any one mean is different. Okay, there is no compulsion that all the means needs to be different in this hypothesis. We just say any mean is different. We don't know. There are three means, right? Three groups. So three groups, any three would be different, three may not be different. We cannot directly just say all three are different right now. So then can we just skip contrast for now? Let's post hoc analysis, just do the post hoc one. Just select bond for anyone and continue. Options, there will be some summarizations, descriptives, means plot. Okay, continue. Okay. So in the output, it will show you an ANOVA table, what we call it as. First, it will give for each of the factor table, low risk wise, how the distribution of data is, mean, how it is, standard deviation, lower bound, upper bound for the mean and the minimum maximum. So you may see low risk में it is 5.6, intermediate में 10 है, high risk में 25, it is gradually increases. Secondly, we have the ANOVA results here. So ANOVA comparison between the groups, that is the important thing we want to look for. And the sum of squares, mean sum of squares, F, these are all the internal statistical things that is calculated. In lot of like thesis perspective or something, people use F test to report and the p value to report from the ANOVA. Yeah, it is important. However, nowadays we can see that the p value can also be reported. But F test is a test here instead of t test. The advance is F test, and based on this, the p value is calculated. It shows significantly difference. So what it means is it is saying that among these three groups, there is a significant difference in the p value in the means. Okay, but we have to make sure which are the mean 1, mean 2 is also different, mean 2, mean 3 is also different, mean 1, mean 3 is also there is a difference or not. This is this overall conclusion of differences we have. So hence I did is a post hoc testing, which is multiple comparisons. So what it has done is low risk compared with intermediate, low risk compared with high, intermediate with low, intermediate with high, high with low, high with intermediate. As like independent t-test it has done, pairwise comparisons, and it has shown me the significant differences among these groups, paired group, two groups, standard error, significance, and the upper bound and lower bound. Okay, so and you can see that the pairs are also significantly different. So mu1 is not equal to mu2, mu1 is not equal to mu3. Similarly, mu2 not equal to mu3, and mu3 is not equal to mu1 or mu2. That's all. Mu is the mean I refer to. Okay. This is the pair, and this is the mean plot, as we always plot means to show the. So it is showing that as the risk increases, PSS also increases. Yeah. So this is the ANOVA. ANOVA can be used for more than 2 groups comparisons. There can be 4, 5, 6, 7, 8, 9. And it gives you opportunity to do the overall comparison among the means from the ANOVA table, and then pairwise comparison as well. And it is very important that you report pairwise comparison when you are using ANOVA, because that gives in-depth information whether each group is significantly different with each other or not. And that's what very important becomes. So
Okay,
is there
good.
any
Good point. So just to cover it up. So again, recap on that. So basically, once fundamentally we are having null hypothesis, and null hypothesis make the comparison between 2 groups. Okay, always having 2 groups. But as we said, the ANOVA can consider 3 groups. That's mean it been considered that 3 groups means are same, and then they are not same. What does it mean they are not same? That's mean either group 1 and group 2 are not same, but group 2 and group 3 are same. Or it could be group 1, group 2, group 3, none of them are same. Or it could be group 2 and group 1 are not same, but group 2 and group 3 are same. So there could be 3 possible ways. So all of them are equal, all of them are not equal, first instance. If they all of them are not equal, then comes that among these 3 inequality, is there 2 of them are equal or only one was the difference? That could also make that 3 of them are not equal, or some first 2 of them are not equal, but last 2 of them are equal. So that's a possibility. So what happens? So once you are having this scenario, ANOVA is good to go, but it raises type 1 error, because the same statistical analysis we are going to go for 2 times, and if you're having more than 3 groups, you would be having multiple times, you will be having inflated type 1 error. To reduce that type 1 error, one of that, as you see that there are many options, and out of Tukey test, HDS, and out of that Bonferroni when the picked over there, because the reason to consider is that Bonferroni is one of the tests that can control this type 1 error, and it's having multiple testing corrections efficiency. That's why Bonferroni being considered. So Bonferroni being considered to control the type 1 error, and then make the comparison between group to group. Group 1 low with intermediate, low with high risk, and intermediate with high risk. So that's the way would stand over there. So yeah, we are almost done now, and next time we will be having again catch up on that. If any of you have any points and comments, so we can quickly now take it.
Yeah, I have a doubt.
Yes.
Yeah, now we just did ANOVA based on one variable, right? And then we defined multi-class, not a binary class. So suppose tomorrow I have 10 dependent and also 10 independent variables, features. So at that time, can we do ANOVA, or is there any other test where we can apply to find the significance?
Yes. So one thing is that 10 independent variable, and then definitely we need to go out from ANOVA. We need to go for statistical model like linear regression model sort of thing. So we will go with that, and we can't compare 10 dependent variable all together, because we need to go, and you would not get any meaningful. There is a way, but you will not get any clinical meaningful interpretation out of that. So out at a time, we need to consider one outcome variable or one dependent variable with 10 or 100 independent variable can be considered. Okay, 100, even not 10, even 100 independent variable could be considered. There is a process by modeling, statistical modeling, that can be done, but not all 10 dependent or outcome variable altogether. One dependent at a time with 100 independent variable could be considered, and that's all largely goes for linear regression model. And then type of your dependent variable, it is a binary, then it will go for logistic model. If it is a non-binary, then linear regression, then generalized linear regression. So all sort of models are being available over there.
Sir, I have one suggestion maybe for this series of sessions we have. Like we have a lot of potential people joining with us, and they are all from various background, maybe oncology, research, PhD, everything. So if and everyone would have their own problems they are dealing with the data, and then this session somehow helping them definitely. But if you have your kind of problems, you can bring up like in a 5 minutes presentation, like this is what you are working on, and this is the how it should be tackled around with statistics or data analysis. And that will definitely help you, but it will help us also to send more methodological things towards all of you, and others will also benefit from it. So if
Yeah,
there
that's
is,
that's a good point. We already having this email exchange and all of you having email ID. So
yeah,
in advance, if you can send your query or some example, we are not asking for real data, but if you can give some gesture of your data, and
of
then
course.
we can definitely try to cover in next classes to sort out your issue and try to give some lights on that. Definitely, that's a good point, Akash.
Yeah, thank you, sir. That would be very interesting to do, because being
Yes.
TMH, TMC centers, we deal a lot of kind of problems, different designs, different results. So that, and it is a lot to learn from. Okay. So in the next session, we'll continue some tests again, and we will start touching upon the design aspects, and we see
Okay.
forward to.
Before concluding, Wendy, do you have any points to say?
Sir, do you have any WhatsApp group for the updates for the upcoming sessions?
Yeah, we have a community build so we will forward the links and add you all in that community where we have these updates, current updates going on. We'll onboard
Okay,
you on
sir.
that
Thank
community
you.
group. Yeah.
Okay.
So thank you all. We'll share this PPT and data in SPSS data as well. All of you collect the SPSS softwares from Ankush there. He will help you with installing the SPSS. And please do analyze, and if there is any problem, please do share on that community group or in mail. Definitely will reply it. Thank you very much.
Thank you, Indira, Akash, Ankush, for arranging all. And let's see you soon.